Welcome to another exercise in the workbook statistics, this time on the topic of multiple linear regressions. Let's have a look at the exercise. Here we have for 5 randomly selected students the final grade, the IQ and the average time spent per week studying has been collected, which gives us this table. So here are 5 students and the 3 values per student. We already notice here we marked them with y and x1, x2, so the grade, the final grade is actually the dependent variable, IQ, study time, the independent ones. Our first task, calculate the linear regression equation that describes the relation between the 3 variables. Second, calculate the coefficient of determination, r squared. And finally, conduct a suitable test to check for a margin of error of 5% whether the estimated model has significant explanatory power. Or in other words, conduct an F-test. Well, let's start with the first part, with the regression coefficients. For this, well, we can start with calculating the vector of coefficients, the b. Because as compared to simple linear regression, we do not use formulas anymore. We're working with matrices, so the result will be a vector with all the coefficients. And we get this vector if we use this following formula, whereas at this point x is the matrix considering all the input data for the independent variables and one column containing only ones for the intercept. Y, on the other hand, is the vector containing the information for the dependent variable. So what do we have here? We have this vector for y, that's all the independent values. Then for the first, all the dependent, for all the independent, this column is for the first independent variable, second independent variable, and this is, as I mentioned, a column containing only ones representing the intercept. Okay, we basically have to just take those two and plug them into this formula. For this, however, we're going to need first of the transpose of x and the inverse of this expression. So we start with our vector of coefficients. Here I have at the left side the first matrix. This is already x transpose times x and thereof the inverse matrix. I skipped the detailed calculations thereof because in this unit I want to focus more on the statistics aspects and less on the mathematical matrix calculations. So here, that's x transpose x, the inverse thereof, times matrix x, times the vector for y. I multiply those two matrices, giving me this sub-result, and then multiply this with the vector y, giving me 3 values. And that's actually what this table represented, the X matrix. The first one is for the intercept. The second one is the slope of the coefficient for the first independent variable. And the third one is the coefficient for the second independent variable. So in other words, we can write our regression equation in the following way. Intercept minus 0.0649 times x1, the first independent, plus 0.1449 x2, the second independent. Well, that already takes care of part 1, or part A. And well, as we can see here, it's a lot of matrix multiplications going on. So once you get this handled and you actually know what is x, what is y, this should work out pretty well. So using this, we can carry on with part B, calculating r squared. So part B, coefficient of determination r squared, follows this formula. So what we can do, we can calculate first off the average of y, and then we need those two as well. So what we're going to do, we take the table as given, that's actually this part here, and we add two rows. The first row containing all the y values squared, that's this part here, and then we're calculating those values here, the y hat squared. So what is this? This is actually if I insert x1 and x2 into my regression line, the one I calculated on the slide before, and I get an estimate for y. That's the y hat. And this estimate for y, I'm going to square. That's this part here. So as a result, those two actually should be close to each other. Well, if I have a good regression going on, then they should be close together. So we see here, well, it's not perfect, but it's also not as bad as one might suspect. And well, then I need 3 additional values, meaning I have to calculate 3 means. I need to calculate the mean of y, that's those parts here. Need to calculate the mean of y squared, that's this part down here, this one. And I need to calculate the mean of the squared estimated y values. So this value here. Because then I have all the 3 values I need for this formula for r squared. So I can just plug these 3 values into this formula, giving me an r squared of 0.4006. So roughly 40%. Meaning my estimation, my regression line, can explain roughly 40% of the variance of the dependent variable, so of the final mark. That's already pretty good, but the question would be, is this good enough? And to answer this question, we're going to conduct an F-test in part C. So if I ask about explanatory power, this translates into conducting an F-test. That's what we're going to do here. For the F-test, we need to calculate our test statistic, which follows this formula. So I need r squared. I have this from the previous slide, roughly 40%. I need k. That's the number of independent variables. Here we have 2 independent variables, so k is 2. And we need the number of observations. That's the 5 students, so n is 5. And I can just introduce all these values into this formula, giving me this result. So I get an F statistic of 0.6683. Well, I have my test statistic. To run a test, I also need a reference statistic. For the F-test, the reference statistic is given as F, K, so here 2, n minus k minus 1, 5 minus 2 minus 1, so 2 as well, and then 1 minus alpha. Alpha, that's the margin of error. We had in the text something of alpha being 5%, so here we have 0.95. So in the table, we're going to look up the value f22 0.95, and there we find a value of 19. So if we do our test, we actually compare test and reference statistic. We see that the test statistic is much smaller than the reference statistic. So we cannot reject the H0 hypothesis. We need to keep this, meaning our model does not have significant explanatory power. And it's mainly due to the very, very few observations. Well, that's basically it. So we did calculate the regression line, we calculated the explanatory power, the R squared, and tested whether this is significant or not with the F-test. So well, I hope you enjoyed this session. I say goodbye and see you next time.